Okay, last set of notes for this unit. Last set of notes for the year. We have 3 properties to talk about today, and these will go with the very last lab that we're going to do, and that'll be Monday. Tomorrow's review, Friday's test. We're almost done. Just got a little bit left. The last 3 properties that we need to talk about are called colligative properties. And a colligative property is one that depends on how many particles are being dissolved in a solution. So different substances that can be dissolved will break down into different amounts of particles. And colligative properties are those that depend or change based on the number of particles that are being dissolved. There are 3 colligative properties. There are 3 things that change based on how many particles have been dissolved in a solution. And the first one is called vapor pressure lowering. We've talked about vapor pressure before. You hopefully remember that vapor pressure is the pressure above a liquid in a sealed container of equilibrium. So when all the other conditions are held the same, like it's the same temperature, you can put a liquid in a container, put the lid on the container, and measure the pressure of the vapor above it. Different substances have different vapor pressures. This was from the phase changes unit when we talked about vapor pressure and boiling point. If you have a solution instead of a pure substance, the vapor pressure is going to be lower than the pure substance. And here's a reminder, the vapor pressure is the pressure caused by a vapor in a closed system. So in other words, in a container with a lid. If you have a solution instead of a pure substance, the vapor pressure of that solution will be lower than it would have been for a pure substance. Vapor pressure is always lower when containing a non-volatile solute. Volatile means that it evaporates, so non-volatile would be something that doesn't evaporate. So if you have a solution containing a solute that won't evaporate, something as simple as salt water, salt does not evaporate, the vapor pressure of that solution would be lower than the vapor pressure of the pure substance. Non-volatile means that it does not vaporize or it does not evaporate. To look at why this occurs, we're going to look at a picture. If we're talking about vapor pressure, we need a container with a lid. There should be a solvent in the container, and in this picture the solvent molecules or particles are represented by the yellow circles. If you had a pure substance, all of the molecules at the surface of that liquid would be the same thing. Maybe you could do these with open circles on your notes packet. All of those particles would be the same substance if it was a pure substance. They would all be the same thing. And depending on what that substance was, it would have a certain vapor pressure, whether it was water, whether it was acetone, whether it was ethanol. Every different substance has its own vapor pressure. But if you take a solute and you dissolve it in that solvent, so now we just take some of those particles and shade them in so that they're solute particles instead. There's no real pattern or amount of solute particles you have to have here. Just pick a random number and shade them in. Now at the surface of our solution, we have 2 different particles. We have solvent particles and we have solute particles. The pink ones, the solute particles, can't evaporate. Maybe it's something like table salt that we've dissolved in water. The solvent particles can still evaporate, but what's happened to the number of them that can evaporate? It's less because there's less room at the surface. We should remember from phase changes that evaporation takes place at the surface of the liquid. And if some of those surface spaces are taken up with something else, there's going to be less evaporation of your solvent. If there's less evaporation, what happens to the amount of pressure above it? It'd be less, because there's less things evaporating to the gas phase. So because vaporization occurs at the surface and the solute is in the way, less solvent vaporizes, so therefore your vapor pressure is lower. And this depends on the number of particles of solute. The more pink ones we were to put at the surface here, the less yellow ones would be able to evaporate. So the more particles you have dissolved, the lower the vapor pressure will be. Speaking of how many particles are being dissolved, let's look at a few examples of things that could be a possible solute. And how would you decide which of those things is going to make more particles? Here's our first example. Table salt, sodium chloride. If we put that into a solvent like water, how many particles would we get? It's important that we know that table salt is ionic, because ionic things break apart in water. So if this compound, Na and Cl, were to break apart, you start with NaCl, which would be one particle, and if you break it apart, how many do you get? 2. You would get 2 separate ions, the Na plus ion and the Cl minus ion. We know that because hopefully we know this compound is ionic. So that would be 2 particles. As a result, what you would see is the vapor pressure being lowered by a factor of 2. Let's look at another one. Magnesium chloride. Again, this is an ionic compound. How might we know that? Because ionic compounds usually are made of what kinds of elements? Metals and nonmetals. If you have one of each, metal and nonmetal, chances are that compound's ionic. So we've got magnesium and we've got chlorine, metal and nonmetal, that's ionic. That means this whole compound's going to come apart if we put it in water. All these examples are for water right now. How many particles would we get? 3. You'd get 1 magnesium ion and 2 chloride ions. So that would be 3 particles. So as a result, you would see your vapor pressure be lower by a factor of 3. But what if the substance we were putting in, what if the solute wasn't ionic? What if it was covalent instead? The sugar that you might put in an iced tea is covalent. Do you remember from your covalent versus ionic lab if the covalent things dissolved? It's been a while, but we did a lab where we had 6 little test tubes and you had different substances. One of them was like mothballs. And you put them in there and you would look to see if they dissolved. The covalent things did not dissolve very well. And you probably know that if you think about trying to put sugar in cold water. It usually just kind of sinks to the bottom. It doesn't dissolve very well. Another thing that's true about covalent particles is that the molecule itself doesn't separate. With the ionic things will break apart into their ions. So however many ions you would have, that's how many particles you would have. Covalent things really don't break apart. the molecules will separate. Molecules that were sitting side by side will separate sometimes, but the molecule itself stays together. So the sugar molecule, this one is glucose, C6H12O6, that molecule stays together. Two molecules sitting side by side can break apart, but the molecule stays whole. So for every molecule that you put in, you only get one particle. So you have to watch out for the difference between the ionic things and the covalent things, because that changes the number of particles that they would make. Property number 2, called boiling point elevation. This property says that a solution will boil at a higher temperature than a pure solvent. So why does that happen? We should remember, it's kind of a good review for your final. We should remember that boiling occurs when vapor pressure equals atmospheric pressure. Vapor pressure is usually pretty low compared to atmospheric pressure. When you heat something, you raise the vapor pressure. When those two pressures are equal, that's when the solution boils. Remember from the phase changes unit, that's when the pressure on the inside of the boiling bubbles can support the pressure from the outside. So that's when the solution boils. We already know that a solution is going to have a lower vapor pressure than the pure solvent. So if the vapor pressure is even lower to begin with, you need more energy to raise the vapor pressure up to atmospheric pressure. And again, this property is proportional to the number of particles you have in the solution. The more particles you have dissolved, the lower the vapor pressure will be, the bigger the difference between vapor pressure and atmospheric pressure. So you'll need more energy to get those two to be equal. This idea brings up an interesting example. Why do you put salt in the water if you're going to make spaghetti? Almost every year somebody tells me it boils faster. This is kind of an old wives' tale. Think about this. If you put salt in the water, that's going to make the boiling point higher because you need more energy for that vapor pressure to equal atmospheric pressure. If you make the boiling point higher, is it going to boil faster? No, but if you have more heat, then theoretically your noodles would cook faster. I've never tried it. I don't know that it would be significant enough to actually make a difference. I kind of doubt it. If you have somebody who's maybe a chef or a little more experienced with food, they actually tell you the reason is just to season the pasta so that you have salt on the pasta when you put it in. But a lot of people think that it makes the water boil faster, and it doesn't. If your water's boiling at a higher temperature, it's not going to boil faster. It's going to boil slower. But the pasta might cook faster by a teeny tiny little bit. Okay, so putting salt in the water does not make the water boil faster. It in fact makes the water boil slower. Although your pasta might cook just a little bit faster, theoretically, because your water would be warmer when it boiled. One more property. This is the best one, called freezing point depression. A solution freezes at a lower temperature than a pure solvent. A solution freezes at a lower temperature than a pure solvent. So why does that happen? If you think about what the molecules or atoms have to do in order to go from a liquid to a solid, they have to get closer together, and they have to line up, usually, in a crystal pattern. Think about freezing water. That's why snowflakes have a six-sided or six-pointed pattern to them, because all the water molecules have to line up in that pattern. If there's something in the water that gets in the way of that pattern, it's going to make it harder for that substance to freeze. So the particles in the liquid disrupt the orderly pattern of the solid crystal, which means that that solution has to get colder to solidify. And again, it's proportional to the number of particles. The more particles you have getting in the way, the colder that solution has to be before it will turn into a solid. Two applications of this that we take advantage of quite often. One would be in the winter. What do you put on the roads?
Salt.
What's the salt do? By lowering the freezing point. The salt gets in between the water molecules and disrupts the pattern of that crystal. So it lowers the freezing point. So that means the water has to be colder to freeze. It does occasionally, especially this winter, get so cold outside that the salt doesn't do any good because it doesn't lower the freezing point enough. It's already colder than that amount. The other reason you might want to melt ice with salt is to make ice cream. If you've ever made homemade ice cream at home, you usually have a big container and the outside is like a ring of ice and you put salt in it, and then the ice cream mix goes on the inside, right? And there's a little paddle on the inside that turns. The salt lowers the freezing point of the ice, which makes the ice melt and makes it colder so that your ice cream can freeze. A couple of points to make here. Sometimes in the winter they put sand on the roads instead of salt, especially if they're running out of salt or they're running out of money. The purpose of that is purely for traction. It does nothing to melt the ice. Sand doesn't dissolve in water, so it's not going to help with the freezing point. What they usually use on the roads is just plain sodium chloride. It's ionic, so it dissolves, melts the ice by lowering the freezing point. But we know that this property is proportional to the number of particles. So theoretically, we could get better results if we picked something that made more particles when it dissolves, such as aluminum chloride. How many particles would you get out of aluminum chloride?
4.
4. That'd be quite a bit better. Problem is, it's not as readily available. Other things are more expensive. So they usually just use plain old table salt. Review tomorrow, test Friday, lab Monday, review for the final, and then the final. We're officially finished.